Hello and welcome. I'm so glad you're here. Right now, wherever you are, I want you to take a moment to settle in. Find a comfortable position. Maybe adjust your pillow, let your shoulders drop, and allow yourself to simply be here in this moment. Tonight, we're going on a gentle journey together, exploring some of the most beautiful mysteries of our universe. We'll talk about light, about stars, and about the shadows they create. These aren't just scientific concepts. They're poetry written in physics, stories told in photons and darkness. So, take a deep breath in and let it out slowly. Let your eyes close if they want to. And let's begin. There's something moving all around you right now. Something so fast that it circles the Earth more than 7 times in a single second. Light. Beautiful, essential light. It pours through your window during the day. It bounces off every surface you see, and it carries information from the farthest reaches of space right to your eyes. But here's something wonderful to consider as you relax deeper into comfort. Light, for all its incredible speed, has a limit. It can only travel so fast and no faster. This is one of the most elegant rules in all of nature. Light moves at exactly 186,282 miles every second. In the metric system, that's 299,792 kilometers per second. Imagine that for a moment. In the time it takes you to snap your fingers, light could travel from here to the moon and partway back. It's almost impossible to picture something moving that quickly. And yet, this speed, as tremendous as it is, represents a cosmic speed limit. Nothing in our universe can move faster than light. Not spaceships, not particles, not even information itself. This discovery changed everything we understand about reality. Albert Einstein, working in a patent office in Switzerland over a century ago, realized something profound. He understood that space and time aren't separate things. They're woven together into something called space-time, and the speed of light is the speed limit of this fabric itself. When something moves very fast, close to the speed of light, time itself begins to slow down for that object compared to everything else. Space contracts. Reality bends. It sounds like science fiction, but it's been proven again and again with atomic clocks on airplanes, with particles in accelerators, with every GPS satellite orbiting above us. Think about what this means for a moment. The light that's reaching your eyes right now from a lamp across the room took only a tiny, imperceptible fraction of a second to arrive. But the sunlight that warmed your face today, that light left the sun about 8 minutes before it touched you. 8 minutes of travel time across 93 million miles of empty space. When you looked at the sun this morning, if you looked safely, of course, you weren't seeing the sun as it is now. You were seeing the sun as it was 8 minutes ago. You were literally looking into the past. And this brings us to something even more beautiful. When you look up at the night sky, every single star you see is a time machine. Every point of light is a messenger from the past, carrying news of distant suns across the vast ocean of space. Let that thought settle in as you breathe slowly, in and out. The universe is so large, and light, even at its incredible speed, takes time to cross it. Lots of time. The nearest star to us, beyond our own sun, is called Proxima Centauri. It's a small, dim red dwarf star, and it sits 4.24 light-years away. That means the light you see from Proxima Centauri tonight left that star 4 years and 3 months ago. You're seeing it as it was in the past, in a time before this moment, shining across the darkness to reach you now. Breathe that in. 4 years of travel for a single photon of light to make the journey. But Proxima Centauri is our close neighbor. Most stars are much, much farther away. The bright star Betelgeuse, the reddish star that marks the shoulder of Orion the Hunter, lies about 642 light-years from Earth. When you look at Betelgeuse, you're seeing light that left that star around the year 1380. The Renaissance hadn't begun yet. Printing presses didn't exist. The light you see tonight has been traveling since medieval times, crossing the incomprehensible emptiness between stars, just to arrive at your eye at this very moment. Polaris, the North Star, the faithful guide that's helped travelers find their way for thousands of years, is somewhere between 323 and 433 light-years away. The uncertainty in that measurement doesn't matter much, because either way, the light you see from Polaris is older than your great-great-great-grandparents. It's older than nations. Some stars you can see with your naked eye are thousands of light-years distant. And through telescopes, we can see galaxies whose light has been traveling for billions of years, since before Earth even existed. Here's something that might give you a moment of peaceful wonder as you sink deeper into relaxation. Some of the stars you see in the night sky, some of those ancient points of light, might not exist anymore. A star could have exploded in a brilliant supernova or quietly faded into darkness. But its light is still traveling toward us, still on that long journey across space. We won't know it's gone until that final light reaches us and then stops coming. The night sky isn't just a map of space. It's a timeline, a living history of the universe spread out above you. Every star is a different chapter, a different moment in cosmic time. And you, relaxing here, breathing slowly, you're looking at all of those moments at once. The universe has arranged itself so that looking outward means looking backward. The farther you look, the older the light, the more ancient the view. When astronomers look at the most distant galaxies through powerful telescopes, they're seeing those galaxies as they were billions of years ago, when the universe itself was young. They're watching light that began its journey before our solar system formed, before the Earth cooled, before the first life stirred in ancient oceans. That light has been traveling all this time, just to be seen, just to tell its story. Let your breathing slow even more as we consider something else, something beautiful and strange. What exactly is this light that travels so far? What is it made of? For a long time, centuries actually, humans debated this question passionately. Some thought light was a wave, rippling through space like water waves through an ocean, spreading out, diffracting around corners, interfering with itself. Others thought light was made of particles, tiny bullets of energy shooting through the void, traveling in straight lines, bouncing off surfaces. Scientists argued for generations, designing clever experiments, gathering evidence for their preferred view. And here's the beautiful, strange truth that eventually emerged from quantum mechanics in the early 20th century. They were both right. Light is both wave and particle, simultaneously, impossibly, wonderfully. Light has a dual nature, something science calls wave-particle duality. It behaves as both a wave and a particle, depending on how you look at it, on what question you ask of it. When light is traveling, spreading out, diffracting around corners, creating interference patterns, it acts like a wave, like ripples on a pond. It has wavelength, the distance between wave crests. It has frequency, how many wave crests pass a point per second. It oscillates as it moves, electric and magnetic fields rising and falling, perpendicular to each other and to the direction of travel, propagating through space at 300 million meters per second. Light waves can interfere with each other. When two waves meet, they add together. If two wave peaks align, they create a bigger peak, constructive interference, brighter light. If a peak meets a trough, they cancel out, destructive interference, darkness. This interference creates patterns, beautiful patterns of light and dark, bright and dim. You can see this in soap bubbles, where light reflects off both the outer and inner surfaces of the thin soap film. The two reflected waves interfere, and depending on the thickness of the film and the wavelength of light, some colors interfere constructively and appear bright, while others interfere destructively and disappear. That's why soap bubbles shimmer with rainbow colors that shift and swirl as the film moves and changes thickness. It's interference, waves of light adding and subtracting, creating beauty through physics. You can see interference in oil slicks on water, in the colors of peacock feathers and butterfly wings, in the coatings on camera lenses that reduce reflections. Interference is everywhere, a fundamental property of waves, and light shows it clearly. But there's a problem. Waves need something to wave in, a medium. Water waves move through water. Sound waves move through air. What does light wave in? Scientists in the 19th century proposed the existence of an invisible substance called the luminiferous ether, filling all of space, providing a medium for light waves. They searched for evidence of this ether, performed experiments to detect Earth's motion through it, and they found nothing. The ether doesn't exist. Light doesn't need a medium. It waves in nothing, in empty space, propagating through the vacuum where there's nothing to propagate in. That should be impossible, but it happens. Light is a wave that needs no medium, a self-sustaining oscillation of electric and magnetic fields, creating each other as they travel. But when light interacts with matter, when it's absorbed by an atom or emitted by one, when it knocks an electron out of a metal surface or excites a molecule, it behaves like a particle. We call these particles photons. They're tiny, discrete packets of electromagnetic energy, quanta of light. Each photon carries a specific amount of energy, and that energy is directly related to the light's frequency. Higher frequency means higher energy. Blue photons have more energy than red photons. Ultraviolet photons have more energy than visible photons. Gamma-ray photons have enormous energy, enough to break apart atomic nuclei. The energy of a photon is given by Planck's equation, E equals h times f, where E is energy, f is frequency, and h is Planck's constant, a fundamental constant of nature, approximately 6.6 times 10 to the negative 34 joule seconds. This equation, discovered by Max Planck in 1900 while studying black-body radiation, was the birth of quantum mechanics. It revealed that energy comes in discrete chunks, quanta, not in a continuous smooth flow, as classical physics assumed. Light is quantized. It exists in photons, indivisible packets of energy. You can't have half a photon or a quarter of a photon. You can have one photon, two photons, three photons, but nothing in between. Energy is grainy at the quantum level, not smooth. Red light has longer wavelengths, around 600 to 700 nanometers, and lower frequency, around 400 to 500 trillion oscillations per second. Blue and violet light have shorter wavelengths, around 400 to 500 nanometers, and higher frequency, around 600 to 750 trillion oscillations per second. And all the colors in between, all the colors of a rainbow, orange, yellow, green, cyan, are just different wavelengths of visible light, different frequencies, different energies of photons reaching your eyes and being interpreted by your brain as color. Each wavelength, each color is a different energy of photon, a different frequency of electromagnetic oscillation. Light is a wave when it needs to be, and a particle when it needs to be, and somehow, mysteriously, it's both at once, underlying both aspects, neither wave nor particle, but something deeper, something we don't have everyday words for. It's as if light knows what we're asking of it and responds accordingly. This isn't magic, of course. It's quantum mechanics, the science of the very small, where things don't behave the way we expect them to, based on our everyday experience with macroscopic objects like balls and cars and planets. At the quantum scale, the rules are different, strange, counterintuitive, beautiful. There's a famous experiment called the double slit experiment, first performed with light by Thomas Young in 1801, though he didn't know about photons yet. Imagine shining light through two narrow slits cut in an opaque barrier, close together, maybe a fraction of a millimeter apart. On a screen behind the barrier, you don't see just two bright lines where the light passes through the slits, which is what you'd expect if light was simply particles. Instead, you see many lines, a pattern of bright and dark bands, alternating stripes spreading out from the center. This is an interference pattern. It happens because light waves from each slit spread out, like ripples from two pebbles dropped in water. These waves overlap, interfere with each other. Where two wave peaks meet, crest aligning with crest, they add together and make a bright band on the screen. Where a peak meets a trough, crest aligning with valley, they cancel out and make a dark band. The pattern of bright and dark stripes is wave behavior, pure and simple, unmistakable. But here's where it gets wonderfully, impossibly strange. If you turn down the intensity of the light source so that photons go through the slits one at a time, so low that only one photon exists between the source and the screen at any given moment, each photon arriving individually, you might expect them to act like particles. Each photon should go through one slit or the other, and you should see two bright regions on the screen where photons land after passing through the slits. But that's not what happens. Even when sent one at a time, the photons still create an interference pattern over time. Each photon lands at one spot on the screen, a single point of light, particle-like. But the distribution of where many individual photons land builds up the same interference pattern you'd get with bright light, the same stripes of bright and dark. It's as if each individual photon somehow goes through both slits at once, interferes with itself, and then lands at a spot determined by that interference. The photon seems to exist in a state of possibility, a quantum superposition, traveling as a wave, exploring all possible paths until the moment it hits the screen and is detected. Then it becomes a particle, a single point of light, a single photon absorbed by a single molecule in the detector or screen. The wave function, The mathematical description of the photon's possible locations and paths collapses into a single actuality when observed. Before observation, the photon is spread out, wave-like, existing in many states at once. After observation, it's localized, particle-like, existing in one definite state. This is measurement, observation, the act of detection, and it fundamentally changes the quantum system. If you try to detect which slit each photon goes through, perhaps by placing detectors at the slits, something even stranger happens. The interference pattern disappears. When you measure which slit the photon passes through, forcing it to be a particle at that moment, to choose one slit or the other, it stops interfering with itself. The pattern on the screen changes from many stripes to just two bright regions, one behind each slit, exactly what you'd expect from particles. The act of measurement changes the outcome. Observing which path the photon takes destroys the interference. This isn't because the measurement apparatus physically disturbs the photon, though it does do that. It's deeper. The act of gaining which path information fundamentally changes what the photon can do. When you don't know which path it takes, it can take both, interfere with itself, create the pattern. When you do know which path it takes one path, acts like a particle, doesn't interfere. Information, knowledge, observation, these change reality at the quantum level. It's bizarre, unsettling, profound. This wave-particle duality is one of the foundations of quantum mechanics, and it tells us something profound about reality. At the smallest scales, at the level of photons and electrons and atoms, nature isn't made of definite things in definite places doing definite things. It's made of probabilities, possibilities, superpositions, quantum states that encompass multiple outcomes simultaneously. The universe at its foundation is probabilistic, not deterministic. Things don't have definite properties until those properties are measured. Before measurement, particles exist in a fuzzy cloud of probability, spread out in space and time. After measurement, they snap into a single definite state, a single position, a single momentum, a single energy. The wave function collapses. Possibility becomes actuality. Light taught us this. Light showed us that the universe is far stranger and more beautiful and more mysterious than we ever imagined when we assumed it followed common sense and everyday experience. Light revealed quantum mechanics to us by being impossible to fully explain with classical physics, by being both wave and particle, by doing things particles shouldn't be able to do, and things waves shouldn't be able to do. And that's a comforting thought in its own way, actually. The universe is full of mystery, full of wonder, full of things that don't fit into neat boxes and simple explanations. Reality is richer than our intuitions, deeper than our initial guesses, stranger than our everyday experience prepared us for. The universe is quantum mechanical at its heart, not just light, but everything. Electrons, protons, atoms, molecules, they all show wave-particle duality. They all exist in superposition until measured. They all interfere with themselves. Quantum mechanics governs all matter and energy, though its strange effects are most obvious at small scales. At large scales, with billions of particles, quantum effects average out, and classical physics emerges as an approximation. But fundamentally, everything is quantum. You're quantum. You're made of particles that are also waves, that exist in superposition, that are governed by probability. Of course, at your scale, with so many particles, the quantum weirdness averages away into classical behavior. But it's there, underlying everything. And we've learned to use this. Quantum mechanics isn't just philosophy or abstract theory. It's technology. Lasers work because of quantum mechanics, because electrons in atoms can be stimulated to emit photons in phase, creating coherent light. LEDs, solar panels, computer chips all depend on quantum mechanics, on the behavior of electrons in semiconductors, on quantum tunneling and band gaps and wave functions. MRI machines use quantum spin, a quantum property of protons in your body's atoms. Quantum mechanics is everywhere in modern life, powering devices we use daily, even if we don't think about the quantum physics underlying them. And scientists are working on quantum computers, devices that use quantum superposition and entanglement to solve certain problems exponentially faster than classical computers. Quantum cryptography promises unbreakable encryption based on the laws of quantum mechanics. The future will be increasingly quantum, leveraging the strangeness of the quantum world for practical benefit. Light showed us the way. Light was the first quantum phenomenon fully understood, and it opened the door to understanding all the others. And when you look at light now, when you see sunlight or starlight or the glow of a lamp, you can know that you're seeing something profoundly strange, something that's both wave and particle, something that exists in superposition until observed, something governed by probability and quantum rules. You're seeing a fundamental mystery of the universe, playing out in every photon reaching your eyes. And that makes light even more beautiful, knowing what it really is, knowing the depth hiding beneath the surface. Light is not just brightness and color. It's a window into the quantum nature of reality, into the deep strangeness of existence itself. As you relax even more deeply, let's consider another gentle mystery. The light you can see, all the colors of the rainbow from deep violet to deep red, all the beauty of a sunset or a starry night, that visible light is only a tiny, tiny fraction of all the light that exists. Most light is invisible to human eyes. We live in an ocean of electromagnetic radiation that we can't see, that passes through us and around us every moment of every day. Your eyes evolved to see only a narrow band of the spectrum, the wavelengths most useful for survival, for finding food and avoiding danger. But the universe produces light across an enormous range of wavelengths, and each part of this spectrum tells a different story, reveals different aspects of reality. The electromagnetic spectrum is vast, spanning wavelengths from kilometers to fractions of the size of an atom. And it's all the same phenomenon, the same thing, electromagnetic radiation, light. It's all waves of oscillating electric and magnetic fields propagating through space at the speed of light. The only difference between radio waves and visible light and gamma rays is wavelength and frequency. Longer wavelengths have lower frequencies and lower energies. Shorter wavelengths have higher frequencies and higher energies. But fundamentally, it's all light. At one end of the spectrum, you have radio waves with wavelengths that can be meters or even kilometers long. These are the waves used for AM radio, FM radio, television broadcasts, and many forms of wireless communication. The AM radio band uses wavelengths around 300 meters. FM radio uses wavelengths around 3 meters. Radio waves are all around you right now, passing through the walls of your house, through your body, completely invisible and unfelt. Your radio or phone can detect them, translating their modulated patterns into sound and images, into music and voices and data. But to your senses, they're completely imperceptible. Radio waves can pass through solid objects easily because their wavelengths are so long compared to the atomic structure of matter. They diffract around buildings and mountains. They reflect off the ionosphere, allowing long-distance communication around the curve of the Earth. Before satellites, radio communication relied on this reflection, bouncing signals off layers of charged particles high in the atmosphere. Radio waves from space also reach Earth, passing through the atmosphere, and radio astronomers use large dish antennas to collect these cosmic radio signals, studying pulsars, quasars, distant galaxies, the cosmic microwave background. Some of the oldest light in the universe, light from just a few 100,000 years after the Big Bang, has been stretched by cosmic expansion into radio waves, and we can detect it with radio telescopes, seeing the universe as it was in its infancy. Move up the spectrum and you find microwaves, with wavelengths from about a meter down to a millimeter. Microwaves are used for radar, for satellite communication, for Wi-Fi and Bluetooth, and, yes, for heating food. Microwave ovens work by emitting microwaves at a specific frequency that water molecules absorb efficiently. The water molecules in food rotate rapidly when hit by these microwaves, and that rotation generates heat through friction. The food heats from the inside out as the microwaves penetrate and excite water molecules throughout. Microwaves from space are important too. The cosmic microwave background, the afterglow of the Big Bang, peaks in the microwave range. It's the oldest light we can observe, radiation that has been traveling through space for over 13 billion years, since the universe was young and hot, since atoms first formed and photons could travel freely. That ancient light has been redshifted, stretched by the expansion of the universe, from visible and infrared wavelengths into the microwave range. Satellites like COBE, WMAP, and Planck have mapped this background radiation in exquisite detail, revealing tiny temperature fluctuations that seeded the formation of galaxies and cosmic structure. The cosmic microwave background is everywhere, surrounding us, a 3-degree Kelvin glow filling all of space, the fading echo of creation. Then comes infrared light, with wavelengths just slightly longer than red visible light, from about 700 nanometers to a millimeter. Infrared is heat radiation. Everything warm emits infrared. Your body glows in infrared right now, radiating heat into the cooler air around you, emitting about 100 watts of infrared power. If you could see in infrared, you would see warm-blooded animals glowing, see the heat rising from pavement on a summer day, see the warm spots where sunlight has heated walls and stones. Infrared cameras reveal heat leaks in buildings, detect people and animals in darkness, show hot engines and machinery. Some animals can detect infrared. Pit vipers have specialized organs on their faces that sense infrared radiation, allowing them to detect the body heat of prey even in total darkness. They can strike accurately at a warm mouse in a pitch-black cave, guided by the infrared glow of its body. Certain beetles can detect infrared from forest fires, allowing them to sense fires from kilometers away and fly toward them. They lay their eggs in burned wood, giving their larvae a head start in the newly opened niche. To these creatures, infrared is as real as visible light is to us. They navigate by heat. Infrared astronomy is valuable because dust clouds that block visible light often allow infrared to pass through. Infrared telescopes can see through the dust in star-forming nebulae, revealing protostars and young stars hidden within. They can see the glow of distant galaxies whose visible light has been redshifted into infrared by cosmic expansion. Infrared observations have revealed planets around other stars, brown dwarfs too cool to shine in visible light, the warm glow of protoplanetary disks. The James Webb Space Telescope, launched in 2021, observes primarily in infrared, allowing it to see the earliest galaxies formed in the universe, to peer into star-forming regions, to analyze the atmospheres of exoplanets. Infrared opens a window to parts of the universe invisible in other wavelengths. After infrared comes the narrow band of visible light, from about 400 nanometers for deep violet to about 700 nanometers for deep red. That tiny range is your window to the electromagnetic universe. 400 nanometers is about the wavelength of the calcium atoms in your bones vibrating. 700 nanometers is about 10 times the size of a typical virus. That's the range your eyes detect, converting photons into electrical signals, into visual perception, into the experience of color and brightness. Human vision evolved to work in this range because it's where the sun emits most of its energy and where Earth's atmosphere is most transparent. It's the range most useful for seeing food, predators, mates, and the environment. But it's a tiny sliver of the full spectrum. Within visible light, different wavelengths correspond to different colors. 400 nanometers is violet, the shortest wavelength humans can see. 450 nanometers is blue. 500 nanometers is cyan or turquoise. 550 nanometers is green. 600 nanometers is orange. 650 nanometers is red. 700 nanometers is deep red at the edge of human perception. Each wavelength stimulates the photoreceptor cells in your retina differently, and your brain interprets those patterns of stimulation as color. Color isn't a property of light itself, exactly. It's a perceptual experience created by your nervous system in response to wavelengths. But the wavelengths are real, objective, measurable properties of electromagnetic radiation. Beyond violet comes ultraviolet light, with wavelengths shorter than violet, from about 400 nanometers down to 10 nanometers. Ultraviolet light is more energetic than visible light, energetic enough to cause chemical reactions, to break molecular bonds. This is why ultraviolet from the sun can damage skin cells, causing sunburn and increasing cancer risk. DNA absorbs ultraviolet light, and the energy can create mutations. But ultraviolet isn't all harmful. It helps your body produce vitamin D when it strikes your skin. Plants and some animals can see ultraviolet. To a bee, flowers look completely different than they do to us, painted with ultraviolet patterns that guide the bee to nectar and pollen. These patterns are invisible to human eyes, but obvious to bees. Flowers have evolved ultraviolet markings specifically to attract pollinators that can see in that range. Ultraviolet light makes certain materials fluoresce, absorbing ultraviolet and re-emitting visible light. This is why white clothes glow under black lights, which emit ultraviolet. Detergents often contain fluorescent brighteners that absorb ultraviolet and emit blue light, making whites appear whiter and brighter. Scorpions fluoresce in ultraviolet, glowing. Bright blue-green, for reasons scientists still don't fully understand. Perhaps it helps them detect light levels or protects them from UV damage. It's a mystery still being explored. The sun emits a lot of ultraviolet light, but most of it is absorbed by Earth's ozone layer high in the atmosphere. Ozone molecules, made of 3 oxygen atoms, absorb ultraviolet efficiently, protecting life on the surface from the most damaging wavelengths. Without the ozone layer, life on land would be difficult or impossible. The ozone layer is why environmental protection of the atmosphere matters. Damage to the ozone layer, caused by chlorofluorocarbons and other industrial chemicals, threatened to increase ultraviolet reaching the surface, increasing skin cancer and cataracts, damaging ecosystems. International action, particularly the Montreal Protocol, helped phase out these chemicals, and the ozone layer is slowly recovering. It's a reminder that human actions can affect global systems and that cooperation can solve environmental problems. Ultraviolet astronomy reveals hot stars, stellar atmospheres, supernova remnants, and the structure of galaxies. Many astronomical objects emit strongly in ultraviolet. Hot, massive stars with surface temperatures above 10,000 degrees emit most of their energy in ultraviolet. Observing in ultraviolet shows us these stars clearly, revealing stellar populations and star formation rates in galaxies. Ultraviolet observations have to be done from space, though, because Earth's atmosphere blocks most ultraviolet light. Satellites like Galaxy and the Hubble Space Telescope's ultraviolet instruments have mapped the ultraviolet sky, revealing the cosmos in wavelengths invisible from the ground. Higher in energy still, we find X-rays, with wavelengths from about 10 nanometers down to 10 picometers, about the size of an atom. X-rays are energetic enough to penetrate soft tissue, but are blocked by denser materials like bone and metal. This is why doctors use X-rays to see inside your body without surgery. An X-ray machine emits X-rays that pass through your body and expose a detector or film on the other side. Soft tissues like muscle and organs absorb some X-rays, but let most pass through, appearing dark on the image. Dense tissues like bones absorb more X-rays, appearing bright. It's shadow imaging, using X-rays instead of visible light. X-rays from space are produced by extremely hot or energetic processes. Gas heated to millions of degrees emits X-rays. Material falling into black holes, and neutron stars heats up and glows in X-rays. Supernova remnants, the expanding shells of gas from exploded stars, emit X-rays as shock waves heat the gas. X-ray astronomy reveals some of the most energetic and violent phenomena in the universe, things invisible in visible light. The Chandra X-ray Observatory, launched in 1999, has captured stunning images of supernova remnants, galaxy clusters, black holes, neutron stars, all glowing in X-ray light. X-rays show us the universe at its most extreme. And at the very highest energies, we have gamma rays, with wavelengths shorter than 10 picometers, smaller than an atomic nucleus. Gamma rays are the most energetic form of light, produced by radioactive decay, by nuclear reactions, by the most violent cosmic events. Supernovae produce gamma rays. Pulsars emit gamma ray beams. Black holes, as they consume matter, emit gamma rays from the jets of particles accelerated to near light speed. Gamma ray bursts, the brightest explosions in the universe, brief flashes of gamma rays lasting seconds to minutes, are thought to come from the formation of black holes or the collision of neutron stars. For a few seconds, a gamma ray burst can outshine all other gamma ray sources in the universe combined. If one occurred close to Earth, it could damage the ozone layer and harm life. Fortunately, they're rare and usually far away. Gamma rays are so energetic they can alter atoms, ionize matter, break apart molecules. They're dangerous to living tissue, which is why gamma radiation is used to sterilize medical equipment and food. But they're also useful. Gamma-ray astronomy reveals the most energetic processes in the cosmos. The Fermi Gamma-ray Space Telescope orbits Earth, mapping the gamma-ray sky, detecting thousands of sources. Gamma rays from space are blocked by the atmosphere, so gamma-ray astronomy must be done from space. These observations teach us about black holes, neutron stars, cosmic rays, the extreme physics of the universe. All of this, from the longest radio waves to the shortest gamma rays, is light. It's all electromagnetic radiation, all photons, all traveling at the speed of light. And you, lying here relaxing, you're bathed in it constantly. Radio waves pass through you from distant transmitters. Microwaves from satellites and cell towers wash over you. Infrared radiates from your skin and from everything warm. Visible light reaches your eyes from the room around you. Ultraviolet from the sun reaches you during the day, some absorbed by your skin, some blocked by the atmosphere. X-rays and gamma rays from space are mostly blocked by the atmosphere, but a few reach the surface. Cosmic rays creating showers of particles in the upper air. You live in a rich electromagnetic environment, most of it invisible, all of it part of the natural universe. And this is just one small corner of the phenomena the universe contains. Light, in all its forms, is only part of the story. There's also matter, particles, fields, forces. There's gravity, space-time, quantum mechanics, the strong and weak nuclear forces. There's dark matter, dark energy, neutrinos, gravitational waves. The universe is far richer and stranger than our narrow sensory window reveals. But light is the messenger that tells us about it all. By studying light, by analyzing its wavelengths and intensities, by observing how it's absorbed and emitted and scattered and bent, we've learned almost everything we know about the cosmos. Light carries the information. Light connects everything across the vastness of space. And that's a beautiful thing, truly beautiful. Light also needs darkness to be understood, and this brings us to shadows. Shadows are light's quiet companion, the negative space that reveals light's presence and behavior. A shadow forms when light encounters something it cannot pass through. Opaque objects block light, and in the space behind them, where light cannot reach, a shadow appears. Shadows are absence, but they're also information. They tell us about the light source, about the object blocking the light, and about the geometry of space. Let yourself relax even deeper as we explore the peaceful science of shadows. Look at shadows on a sunny day, and you'll notice they have structure. The darkest part of a shadow is called the umbra, from the Latin word for shadow or shade. This is the region completely blocked from the light source. But shadows often have a lighter, fuzzier edge called the penumbra, meaning almost shadow. The penumbra forms because most light sources aren't single points. The sun, for example, is a large disk in the sky, about half a degree across as seen from Earth. Some parts of the sun are blocked from certain areas behind an object, while other parts aren't, creating a gradient from full shadow to full light. This gradient is gentle, soft, like the blending of night into day during twilight. Think about standing under a tree on a bright afternoon. The shadows cast by individual leaves overlap and create dappled patterns on the ground. In the spaces where leaves fully block the sun, you see dark umbral shadows. Where leaves partially block sunlight, allowing some rays through while blocking others, you see lighter penumbral regions. The interplay creates a constantly shifting mosaic as wind moves the branches, as the sun travels across the sky, as light and shadow dance together in peaceful rhythm. Ancient poets wrote about these dappled shadows, about the way light filters through forest canopies, creating sanctuaries of coolness and calm. Shadows aren't just absence, they're art. Shadows also change length and direction as the light source moves. In the morning, when the sun is low on the horizon, shadows are long and stretched out, dramatic and striking. A person standing at sunrise might cast a shadow 10 or 15 times their own height, extending across the landscape like a giant. At noon, when the sun is high overhead, especially in tropical regions near the equator, shadows are short and squat, hiding beneath the objects that cast them. A person's shadow at noon might be barely larger than their feet. In the evening, shadows lengthen again, pointing in the opposite direction, stretching toward the east as the sun sinks in the west. This daily rhythm of shadow length has a mathematical precision to it, governed by the angle of the sun above the horizon and the simple geometry of light traveling in straight lines. Ancient humans noticed this pattern, of course, and used it to tell time. Sundials, some of the oldest timekeeping devices humans ever created, cast shadows that move in predictable ways as Earth rotates. The gnomon, the part of a sundial that casts the shadow, points toward the celestial pole, and as the sun appears to circle the sky, the gnomon's shadow sweeps across the dial face, marking the hours. Different cultures designed different styles of sundials. Horizontal sundials lay flat on the ground. Vertical sundials stood upright on walls. Equatorial sundials aligned with Earth's equator. All of them translated the sun's apparent motion across the sky into the passage of time, using nothing more than light and shadow. There's something meditative about watching shadows move. They shift so slowly you can't see them moving moment to moment. Yet over minutes and hours their progress is undeniable. It's like watching the tide come in, or grass grow, or clouds drift. The shadow of a sundial gnomon creeps across the dial face at about 15 degrees per hour, the same rate Earth rotates. Watching that shadow move connects you directly to the rotation of the planet beneath your feet. You're seeing Earth turn, revealed through the simple interaction of sunlight and an opaque object. It's profound when you think about it, lying here relaxed and calm. Shadows prove something fundamental about light. They prove that light travels in straight lines, at least through uniform, transparent media like air or empty space. If light could bend around corners on its own, without any external force or curved space-time, shadows would blur and distort in unpredictable ways. But shadows have sharp edges, in the umbra at least, because light rays travel in straight paths. When an object blocks those straight-line paths, the shadow mirrors the object's outline. This is called rectilinear propagation, and it's a basic property of light. Artists understood this long before scientists formalized it. Renaissance painters studied shadows carefully, learning how to depict them accurately to create the illusion of three-dimensional space on flat canvases. They knew that shadows obeyed rules, that they fell in predictable directions, that they revealed the shape and position of objects in space. Shadows also tell us about the nature of the object casting them. A sphere casts a circular shadow. A cube casts a square shadow, though the shape can appear distorted depending on the angle of the light. Complex objects cast complex shadows, and translucent objects, objects that let some light through while blocking the rest, cast softer shadows with less contrast. A frosted glass window creates a diffuse, gentle shadow. A clear glass window barely casts a shadow at all because most light passes through it unobstructed. Colored glass casts colored shadows, filtering certain wavelengths while allowing others to pass. Hold a piece of red glass in sunlight and it casts a dimmer shadow with a reddish tint because it absorbs most wavelengths except red. Shadows exist at every scale. You cast a shadow when you stand in sunlight. A tree casts a shadow that pools beneath its branches, providing a cool refuge on hot summer days. Buildings cast shadows that creep across streets and sidewalks, moving as the day progresses, turning bright plazas dark and dark alleys bright. Skyscrapers cast shadows that can be blocks long in the morning and evening, affecting the sunlight reaching entire neighborhoods. City planners have to consider shadows when designing buildings, ensuring that parks and public spaces receive enough sunlight throughout the day. Mountains cast shadows across valleys. In the morning, the eastern slopes glow with sunlight, while the western slopes remain in shadow. In the evening, the opposite occurs. Entire valleys can be shadowed by mountain ranges, creating microclimates where temperatures stay cooler and moisture lingers longer. Some deep valleys in polar regions remain in shadow for months during winter, never seeing direct sunlight until spring returns. These are places where shadows dominate, where light is the visitor, not the resident. Clouds cast shadows on the ground below, and you can sometimes see them moving like dark ships across the land. From an airplane, you can watch your plane's shadow race along the ground beneath you, surrounded by a glory, a rainbow-like halo caused by light diffracting around water droplets in the clouds. The shadow of a cloud passing overhead brings a momentary cooling, a brief respite from the sun's heat. Farmers learn to read cloud shadows on their fields, watching weather patterns move across the landscape. Even Earth itself casts a shadow, a long cone of darkness stretching out into space away from the sun. This shadow extends nearly 1 million miles behind Earth, tapering to a point. And because the moon orbits Earth, roughly once a month, the moon passes through this shadow or comes close to it. When the moon enters the penumbra, the outer part of Earth's shadow, it dims slightly, though the effect is subtle. When it enters the umbra, the full shadow, the moon darkens dramatically. This is a lunar eclipse, and it's a beautiful, peaceful event to witness. During a total lunar eclipse, the moon doesn't disappear entirely. Instead, it often turns a deep, coppery red, sometimes called a blood moon. This happens because Earth's atmosphere acts like a lens, bending sunlight around the edges of the planet and into the shadow. This bent light is mostly red, because blue light scatters away in Earth's atmosphere, the same reason our sky is blue and our sunsets are red. So the moon, sitting in Earth's shadow, is illuminated by this reddish light that's been filtered and bent through the atmosphere of our entire planet. It's seeing all of Earth's sunrises and sunsets at once. All that red light scattered into the shadow. And we, watching from Earth, see the moon glow in that ancient dusky light. Lunar eclipses can last for hours. The moon moves slowly through Earth's shadow, taking its time. You can watch the curved edge of Earth's shadow creep across the moon's face, proving, as ancient Greeks realized, that Earth is round. Only a spherical object casts a round shadow from every angle. This observation, combined with other evidence, convinced ancient astronomers that Earth was a sphere, not a flat disk. Shadows revealing the shape of worlds. And Earth isn't the only world that casts shadows. The moon casts a shadow too, a smaller one, and when that shadow falls on Earth, we experience a solar eclipse. The moon passes directly between Earth and the sun, blocking the sun's light. From space, you would see a dark spot, the moon's umbra, racing across Earth's surface at over 1,000 miles per hour. This spot is only about 70 miles wide, maybe 150 at most, because the moon is smaller than Earth, and its shadow tapers as it stretches from moon to Earth. If you're standing in the right place at the right time, if you're in the path of that shadow, you can look up and see one of nature's most spectacular events. A total solar eclipse begins slowly. The moon, moving in its orbit, starts to cover the sun from one side. It looks like a bite has been taken out of the solar disk. As more and more of the sun is covered, the light on the ground takes on an eerie quality. Colors become muted. The air cools noticeably. Shadows become sharper because the sun is becoming smaller as a light source, more like a point than a disk. Animals behave strangely. Birds go quiet, thinking night is falling. Crickets start chirping. Dogs and cats become nervous or excited. Then, as the last sliver of sun disappears, totality arrives. The sky darkens dramatically, not to full night, but to a deep twilight. Stars and planets become visible. The horizon glows with a 360-degree sunset, because you're standing in the moon's shadow, but the areas outside the shadow are still in sunlight. And most breathtakingly, the sun's corona becomes visible. The corona is the sun's outer atmosphere, a halo of superheated plasma extending millions of miles into space. It's always there, but normally the sun's bright surface, the photosphere, outshines it completely. Only during a total solar eclipse, when the moon blocks the photosphere, can we see the corona with the naked eye. It appears as a pearly white glow, with delicate streamers and loops extending outward, shaped by the sun's magnetic field. It's ethereal, otherworldly, beautiful beyond description. Totality doesn't last long. The moon is moving, and the shadow is moving, and soon the sun begins to peek out from behind the moon. A brilliant point of light appears, the diamond ring effect, so bright it seems to flash. Then the partial phases resume in reverse, and the eclipse ends. But for those few minutes of totality, you've witnessed something profound. You've stood in the moon's shadow. You've seen the sun's hidden atmosphere. You've experienced a cosmic alignment that happens rarely at any given location on Earth. Solar eclipses are so moving that people travel the world to see them, chasing shadows across continents. The fact that we can see total solar eclipses at all is a cosmic coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away. This means they appear almost exactly the same size in our sky. The moon can just barely cover the sun during a total eclipse. If the moon was smaller or farther away, it would never completely cover the sun. If it were larger or closer, eclipses would be less dramatic, with the moon easily covering the sun with room to spare. But the sizes and distances are balanced perfectly for now. The moon is slowly moving away from Earth a few centimeters per year, and in the distant future, hundreds of millions of years from now, it will be too far away to produce total solar eclipses. Future generations, if they exist, will only see partial eclipses and annular eclipses, where the moon is too small to cover the sun completely. We live in an era where total solar eclipses are possible. It's a gift of timing. Other planets experience eclipses too, though they're different from ours. Mars has two tiny moons, Phobos and Deimos, and they cast small, quick shadows on Mars's surface. From the Martian ground, you would see them pass in front of the Sun as small dark spots, not covering it completely. Jupiter's large moons cast shadows on Jupiter's clouds, dark circles that move across the planet's face. These shadow transits can be photographed from Earth with telescopes. Saturn's rings cast enormous shadows on the planet below, and the planet casts shadows on the rings. When Saturn's rings are edge-on to the Sun, the shadows disappear briefly. When they're tilted, the shadows become striking, creating dramatic contrasts on the planet's surface. And beyond our solar system, astronomers use shadows to find planets around other stars. When a planet passes in front of its star from our point of view, it casts a shadow, or more accurately, it blocks a tiny fraction of the star's light. This causes the star to dim slightly, a dip in brightness that sensitive telescopes can detect. This method, called the transit method, has been used to discover thousands of exoplanets. We can't see these distant planets directly, not yet, but we can see their shadows, the tiny dimming they cause as they pass in front of their suns. Shadows revealing the existence of worlds light years away. Shadows remind us that light always travels true. It doesn't waver or curve on its own in empty space. It goes in straight lines from source to destination, and anything in the way creates darkness on the other side. There's something honest about that, something reliable. Light can be trusted to behave predictably, and shadows are the proof. They're the silent testimony to light's journey, the negative space that defines the positive. Without shadows, we couldn't appreciate light fully. Without darkness, brightness would have no meaning. They're partners, not opponents. They exist together, defining each other, creating the contrast that lets us see the world. But what creates light in the first place? Where does starlight come from? Stars aren't just distant suns burning like campfires in the night. They're nuclear furnaces, vast spheres of plasma where atoms are crushed together with such force that they fuse into new elements, releasing tremendous amounts of energy in the process. This is the engine that powers every star in the universe, including our own sun. And it's one of the most elegant processes in nature. Let your mind rest on this as we explore how stars create light from matter itself. Deep in the core of a star, hydrogen, the lightest and most abundant element in the universe, exists under unimaginable conditions. The pressure is millions of times greater than the pressure at the bottom of Earth's deepest ocean. If you could somehow take a cubic centimeter of material from the sun's core and bring it to Earth, it would weigh about 150 grams, roughly the weight of a baseball, despite being the size of a sugar cube. That's how compressed matter becomes in a stellar core. And the temperature is staggering, around 15 million degrees Celsius. At this temperature, atoms are stripped completely of their electrons, leaving bare nuclei, protons, speeding around in a dense, chaotic soup of plasma. Everything is moving at tremendous speeds, colliding constantly. Normally, protons repel each other strongly. They're all positively charged, and like charges push apart with a force that grows stronger the closer they get. This electrical repulsion is powerful, much stronger than gravity at the scale of individual particles. In normal conditions, protons bounce off each other, unable to get close enough to touch. But in the extreme conditions of a stellar core, protons are moving so fast, with so much kinetic energy, and pressed so close together by the immense gravitational pressure that occasionally they overcome this repulsion. They collide with enough force to get within range of the strong nuclear force, one of the four fundamental forces of nature. The strong force is incredibly powerful, but has a very short range. It only works when particles are essentially touching. When two protons get close enough, the strong force grabs them and binds them together, overpowering the electrical repulsion. But two protons alone are unstable. Almost immediately, one of them transforms. Through the weak nuclear force, another fundamental force, one proton converts into a neutron, releasing a positron, the antimatter version of an electron, and a neutrino, a nearly massless particle that barely interacts with anything. The positron quickly encounters an electron, and they annihilate each other, converting their mass into energy, into gamma-ray photons. The neutrino escapes, racing out of the sun at nearly the speed of light, passing through all the matter between it and the surface, as if it weren't even there. Neutrinos are so weakly interacting that they can pass through light years of lead without being stopped. Right now, billions of neutrinos from the sun are passing through your body every second, and you don't feel a thing. They're ghostly messengers from the core. What remains after this transformation is a deuterium nucleus, one proton and one neutron bound together. Deuterium is heavy hydrogen, a rare isotope, and it doesn't stay alone for long. Another proton crashes into it, fusing with it to form helium-3, a nucleus with two protons and one neutron. This releases another gamma-ray photon. Then two helium-3 nuclei collide and fuse, forming helium-4, the common, stable form of helium with two protons and two neutrons. This final step releases two extra protons back into the plasma, where they can start the cycle again. It also releases more energy. The net result of this whole chain of reactions, called the proton-proton chain, is that four hydrogen nuclei combine to make one helium nucleus. And here's the key. If you could weigh four hydrogen nuclei and then weigh the helium nucleus they create, you'd find the helium weighs slightly less. About 0.7% of the mass goes missing during the fusion process. Four hydrogen nuclei together weigh about 6.69 times 10 to the negative 27th kilograms. The resulting helium nucleus weighs about 6.64 times 10 to the negative 27th kilograms. The difference, about 0.05 times 10 to the negative 27th kilograms, seems tiny. But it's not gone. It's been converted into energy according to Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. Because the speed of light is such a large number, about 3 times 10 to the 8th meters per second, and because it's squared, making it 9 times 10 to the 16th, even a tiny amount of mass converts into an enormous amount of energy. That missing 0.05 times 10 to the negative 27th kilograms of mass from a single fusion reaction becomes about 4.5 times 10 to the negative 12th joules of energy. That still sounds small, but remember, the sun is fusing 600 million tons of hydrogen into helium every single second. Every second, 600 million tons. That's the mass of about 2 million blue whales, converted from hydrogen to helium, with a fraction of that mass becoming pure energy. 4 million tons of mass are completely converted to energy every second in the sun's core, and it's been doing this for nearly 5 billion years. The Sun formed from a collapsing cloud of gas about 4.6 billion years ago, and it ignited nuclear fusion in its core shortly after. Since then, it's been steadily fusing hydrogen, pouring light and heat into space, warming the planets, making life possible on Earth. And it can keep going for about another 5 billion years, until the hydrogen in its core is exhausted. Stars are efficient, patient engines. They don't burn explosively, consuming all their fuel at once. They burn slowly, steadily, converting mass into light and heat, holding themselves up against gravity's crushing pull through the outward pressure of all that energy being released in their cores. It's a delicate balance, and it's maintained automatically. If the fusion rate increases and the core produces more energy, the star expands slightly, the core cools a bit, and the fusion rate decreases. If the fusion rate drops, the core contracts, heats up, and fusion increases again. The star regulates itself, like a living thing maintaining homeostasis. The energy released in the core, those gamma-ray photons produced by fusion and matter-antimatter annihilation, don't immediately escape into space. The Sun's core is incredibly dense, packed with particles. A gamma-ray photon travels only a fraction of a millimeter before it collides with an electron or a nucleus. It's absorbed, giving its energy to that particle, which then re-emits another photon, usually at a slightly lower energy, a slightly longer wavelength. That new photon travels a tiny distance and gets absorbed and re-emitted again. This process repeats millions upon millions of times. The photon bounces around randomly in what's called a random walk, slowly working its way from the core toward the surface. This journey takes an incredibly long time. A single photon, or rather the energy of a single photon, might take anywhere from 10,000 to 100,000 years to migrate from the core to the surface. Think about that. The light warming your face today, the sunlight that made yesterday's sunset beautiful. That light began its journey as energy released in the sun's core tens of thousands of years ago, long before recorded human history, back when our ancestors were still hunter-gatherers living in small tribes. That energy has been bouncing around inside the sun all this time, gradually working its way outward, losing energy with each interaction, being downshifted from gamma rays, through X-rays, through ultraviolet, and finally into the visible light and infrared we see and feel. By the time a photon reaches the sun's surface, the photosphere, it's lost most of its original energy. The surface of the sun is much cooler than the core, only about 5,500 degrees Celsius. At this temperature, matter still glows brilliantly, but it glows mostly in visible light, the light our eyes evolved to see. The photons escape into space, streaming outward in all directions, some of them heading toward Earth. 8 minutes later, traveling at the speed of light across 93 million miles, they arrive. They enter Earth's atmosphere, scatter in the air, creating our blue sky. Some reach the ground, warming the soil, powering photosynthesis in plants, evaporating water to make clouds and rain, driving the weather systems that shape our world. All of this powered by nuclear fusion in the sun's core, by the transformation of hydrogen into helium, by the conversion of tiny amounts of mass into vast quantities of energy. Different stars fuse hydrogen at different rates. Massive stars, much larger than our Sun, have higher core temperatures and pressures. They fuse hydrogen much faster, burning through their fuel in just millions of years rather than billions. A star 10 times the mass of the Sun might live only 20 million years. A star 50 times the Sun's mass might last only a few million years. These massive stars shine brilliantly, bright blue or white, pouring out enormous amounts of light. They're visible from great distances, beacons in the galaxy. But their lives are brief by stellar standards. Smaller stars, red dwarfs like Proxima Centauri, are cooler and dimmer. Their cores are still fusing hydrogen, but at a much slower rate. They sip their fuel gradually, stretching it out over trillions of years. Red dwarfs are the most common type of star in the galaxy, making up about 70% of all stars. They're small, dim, hard to see without telescopes. But they're patient and long-lived. Some red dwarfs born near the beginning of the universe, 13 billion years ago, are still in their infancy, having burned less than a tiny fraction of their hydrogen. They'll still be shining long after the Sun has died, long after most other stars have exhausted their fuel. In the far future, in hundreds of billions or even trillions of years, the universe will be a much darker place, lit mostly by the faint red glow of these ancient red dwarf stars. Our Sun is in between, a yellow dwarf, medium-sized and middle-aged. It's been fusing hydrogen for nearly 5 billion years, and it has about 5 billion more to go. That's its main sequence lifetime, the stable phase where it lives now. But eventually, the hydrogen in the core will run out. The core will be mostly helium, the ash of hydrogen fusion. And with no more hydrogen to fuse, the energy generation in the core will stop. But fusion doesn't just make light and helium. As stars age and evolve, they begin to fuse heavier elements, climbing the periodic table step by step. When a star like the Sun exhausts the hydrogen in its core, fusion stops there, but hydrogen fusion continues in a shell around the helium core. The helium core, no longer supported by fusion pressure, contracts under gravity. As it contracts, it heats up. Eventually, if the core gets hot enough, around 100 million degrees, helium fusion ignites. Helium nuclei, helium-4 nuclei specifically, fuse together in a process that requires higher temperatures and pressures than hydrogen fusion. 3 helium nuclei fuse to form carbon-12. This is called the triple alpha process, because helium nuclei are also called alpha particles. It's a delicate process, requiring 3 helium nuclei to come together almost simultaneously, but in the dense core of an aging star, it happens constantly. Carbon-12 can then capture another helium nucleus to form oxygen-16. So helium fusion produces carbon and oxygen, the fundamental building blocks of organic chemistry, the elements essential to life as we know it. Every atom of carbon in your body was made inside a star through helium fusion. The carbon in your DNA, in your proteins, in the carbon dioxide you exhale, all of it was forged in a stellar core billions of years ago, when an ancient star fused helium into carbon. That star eventually died, and its material was scattered into space, eventually becoming part of the molecular cloud that collapsed to form our solar system. The carbon became part of Earth, part of the molecules that make up living things, part of you. You're carrying the ashes of helium fusion inside you. Stars more massive than the Sun can fuse even heavier elements. After helium is exhausted, if the star is massive enough, the core contracts and heats up again until carbon fusion ignites. Carbon fuses to form neon, magnesium, and other elements. Then, if the star is still more massive, neon fusion begins, producing oxygen and magnesium. Oxygen fusion creates silicon, sulfur, phosphorus. Silicon fusion creates elements near iron. Each stage of fusion requires higher temperatures and pressures, releases less energy, and happens faster than the previous stage. A massive star might fuse hydrogen for millions of years, helium for hundreds of thousands of years, carbon for hundreds of years, neon for a few years, oxygen for a few months, and silicon for just a few days. The star becomes layered like an onion, with shells of different elements fusing at different depths. Hydrogen fuses in the outermost shell, helium below that, carbon deeper still, all the way down to a core of silicon fusing into iron. And iron is where it stops. Iron is the most stable nucleus. Fusing iron into heavier elements doesn't release energy. It requires energy. Fusing lighter elements releases energy because the resulting nucleus is more tightly bound, more stable. That difference in binding energy is released as light and heat. But iron sits at the peak of the binding energy curve. Nuclei lighter than iron release energy when fused. Nuclei heavier than iron release energy when split, when undergoing fission. Iron itself neither benefits from fusion nor fission. It's the most stable configuration, and trying to fuse it costs more energy than it produces. So when a massive star's core fills with iron, fusion ends. The core is no longer generating energy. Without that outward pressure to hold it up, gravity wins. The iron core, now unsupported, collapses. And it collapses fast. In less than a second, the core shrinks from the size of Earth to about 20 kilometers across, a sphere roughly the size of a city. The density becomes so extreme that protons and electrons are crushed together into neutrons. The core becomes a neutron star, one of the densest objects in the universe. A teaspoon of neutron star material would weigh about 1 billion tons. Neutrons, normally unstable when alone, are packed so tightly together that they can support each other through neutron degeneracy pressure, a quantum mechanical effect. The outer layers of the star, still falling inward, crash onto this newly formed neutron core. They encounter a surface so hard, so incompressible, that they bounce. The rebound creates a shockwave that races outward through the star. This shockwave heats and compresses the infalling material, reigniting fusion in the outer layers. Not the slow fusion of a stable star, but explosive fusion happening in seconds. Elements are formed and destroyed, recombined, transformed, and the shockwave blows the star apart. The star explodes in a supernova, one of the most violent and energetic events in the universe. For a brief time, a few weeks, the dying star outshines its entire galaxy, releasing as much energy in that short time as the sun will release over its entire 10 billion year lifetime. And in that explosion, in the intense heat and pressure, elements heavier than iron are forged. Gold, silver, platinum, lead, uranium, all the elements beyond iron on the periodic table, are created in supernova explosions or in collisions between neutron stars. These heavy elements can't be made in the slow fusion of a star's core. They require the extreme conditions of a cosmic catastrophe. So every atom of gold in a wedding ring, every atom of silver in a coin, every atom of uranium in nuclear fuel was created in a supernova or neutron star collision. These elements are rare, precious in more ways than one. They are the products of stellar death, forged in the final moments of massive stars or in the violent mergers of dead stellar remnants. Then those elements are scattered into space, riding the shockwave, enriching clouds of gas and dust, seeding the interstellar medium. New stars form from those enriched clouds, stars that inherit the heavy elements from previous generations. Planets coalesce from the leftover material, rocky planets made of silicon, iron, magnesium, oxygen, carbon, nitrogen, all the elements created in stars and supernovae. Planets like Earth, rich with heavy elements, diverse in chemistry. And eventually, on at least one of those planets, life emerges. Life that uses carbon for its structure, oxygen for its metabolism, iron for its blood, calcium for its bones, phosphorus for its DNA, nitrogen for its proteins. All the gifts of ancient stars. You are made of stardust. This isn't metaphor or poetry, though it sounds like it. It's literal truth. Every atom in your body except hydrogen, and even some of your hydrogen, was reprocessed through stars. Every atom heavier than hydrogen was made inside a star through nuclear fusion, or in a supernova explosion, or in a neutron star collision. The iron in your blood, which carries oxygen through your veins, was forged in the core of a massive star and scattered into space when that star exploded. The calcium in your bones, which gives them strength, was created in a supernova. The oxygen you're breathing right now, which your cells use to generate energy, was made by helium fusion in a giant star. The carbon that forms the backbone of every organic molecule in your body, that was created in the cores of red giants. The stars had to live and die so you could exist. Multiple generations of stars, living and dying and enriching the galaxy, creating the elements necessary for rocky planets and complex chemistry and ultimately life. You're the universe looking at itself, made of star matter arranged in a way that can think and wonder and dream. And relax here, peacefully contemplating its own origins. You're a temporary pattern in the cosmic flow, a brief arrangement of matter and energy that has the gift of awareness, the ability to understand, at least partially, where it came from and what it's made of. And that's extraordinary. Let that settle into your mind as you relax even deeper. You are ancient. You are cosmic. You are connected to everything that has ever been. And the light shining in the sky, the light from those same types of stars that made you, is family in a sense. It's all part of the same grand story. Stars have life cycles, just like living things, though on timescales almost impossible to comprehend. Stars are born, they live, and they eventually die, though their deaths are rarely quiet. Let's walk through a star's life together, slowly, peacefully, as you continue to relax and breathe. Stars begin in nebulae, vast clouds of gas and dust floating in the space between existing stars. These clouds are mostly hydrogen, with a little helium and traces of heavier elements. They can be light years across, dark and cold, barely above absolute zero. But gravity is patient. Even in these diffuse clouds, gravity is gently pulling, gathering material together. If a cloud is large enough, or if it gets a push from a nearby supernova shockwave or stellar wind, parts of it begin to collapse. As material falls inward, it heats up. Gravity converts potential energy into heat. The cloud fragments into smaller, denser clumps, and each clump continues to collapse. At the center of a collapsing clump, temperatures and pressures rise. When the core temperature reaches about 10 million degrees, hydrogen fusion ignites. The clump stops collapsing. It stabilizes. A star is born. This is the main sequence phase, the longest and most stable part of a star's life. Our Sun has been a main sequence star for nearly 5 billion years. and it will remain one for about 5 billion more. During this time, it fuses hydrogen into helium in its core, shining steadily, warming its planets, supporting life on Earth. But eventually, the hydrogen in the core runs out. Fusion stops, at least in the core. The core, now mostly helium, contracts and heats up. Hydrogen fusion begins in a shell around the core, and the energy released causes the star's outer layers to expand. The star swells into a red giant, growing hundreds of times larger, though its surface cools and reddens. Our sun will become a red giant one day. It will expand to engulf the inner planets, possibly even Earth. But that's billions of years away, so there's no need to worry. It's a peaceful, distant future. In the core of a red giant, if the star is massive enough, temperatures rise until helium fusion ignites. Helium fuses into carbon and oxygen, releasing more energy, and the star stabilizes again for a time. But helium burns faster than hydrogen. This phase doesn't last as long. When the helium runs out, medium-sized stars like the Sun don't have enough mass to fuse carbon. The core contracts and the outer layers puff away into space, creating a beautiful structure called a planetary nebula. Despite the name, these have nothing to do with planets. They're shells of glowing gas expanding away from the dying star, lit from within by the ultraviolet light of the exposed core. That core, now naked and no longer fusing anything, is called a white dwarf. It's incredibly dense, about the size of Earth, but with the mass of the Sun. A teaspoon of white dwarf material would weigh several tons. The white dwarf shines not from fusion, but from leftover heat, gradually cooling over billions of years, eventually fading to a cold, dark cinder called a black dwarf. Though the universe isn't old enough yet for any white dwarfs to have cooled completely, every white dwarf out there is still glowing, still slowly releasing the heat from its long-dead fusion fires. But more massive stars have a different fate. If a star is more than about 8 times the mass of the Sun, it can fuse carbon. And once it does, it doesn't stop. Carbon fuses to neon and magnesium. Neon fuses to oxygen. Oxygen fuses to silicon. Silicon fuses to iron. The star becomes layered like an onion, with shells of different elements fusing at different depths, all surrounding a growing core of iron. This process happens fast. A massive star can go from igniting carbon fusion to having an iron core in just a few thousand years, a blink of an eye on cosmic timescales. And then, as we discussed earlier, the iron core collapses. In less than a second, the core shrinks from the size of Earth to about 20 kilometers across. Protons and electrons are crushed together into neutrons. The core becomes a neutron star, one of the densest objects in the universe, so dense that a sugar cube-sized amount of neutron star material would weigh as much as a mountain. The outer layers of the star collapse onto this neutron core and then rebound in a supernova explosion, one of the brightest events in the universe. Supernovae are violent, yes, but they're also creative. They forge heavy elements and scatter them into space. They compress nearby gas clouds and trigger new star formation. They enrich the galaxy with the raw materials for planets and life. And they leave behind exotic remnants. Neutron stars, spinning rapidly, sometimes beaming radiation from their magnetic poles like cosmic lighthouses. We call these pulsars, and they pulse with precise regularity, some spinning hundreds of times per second. If the core is even more massive, even a neutron star can't hold it up. The core collapses past the neutron star stage into a black hole. a region of space where gravity is so strong that not even light can escape. The escape velocity exceeds the speed of light, and since nothing can go faster than light, nothing can get out. Black holes aren't holes in the usual sense. They're objects, incredibly dense singularities surrounded by an event horizon, the boundary beyond which escape is impossible. Light that crosses the event horizon is lost forever, spiraling inward, adding to the black hole's mass. Black holes are silent and invisible, but we can detect them by their effects. Matter falling toward a black hole heats up and emits X-rays. Black holes at the centers of galaxies can be millions or billions of times the mass of the Sun, and they power quasars, the brightest sustained sources of light in the universe. And recently, we've even taken pictures of black holes, or rather, pictures of the glowing gas swirling around them, silhouetting the event horizon against the light. Stars live, stars die, and in their deaths, they give birth to the next generation. Gas expelled from dying stars mixes with the interstellar medium. New stars condense from that enriched material. Those stars live and die, and the cycle continues. Every generation of stars seeds the galaxy with more heavy elements, making the universe more complex, more interesting, more capable of forming rocky planets, and, eventually, life. We're living in a universe refined by countless stellar generations, a universe where the ashes of ancient stars have become us, and light connects it all. Light carries information about distant stars. Light reveals the composition of nebulae through spectroscopy, the study of light broken into its component wavelengths. Each element, when heated, emits light at specific wavelengths, creating a unique fingerprint. By analyzing starlight with spectrographs, astronomers can determine what stars are made of, how hot they are, how fast they're moving, whether they're approaching or receding. Light is information, encoded in wavelength and intensity. Light shows us black holes by illuminating the gas around them, making the invisible visible through its effects on visible matter. Light is the messenger, the universal language of the cosmos. And we've learned to read that language over centuries of observation to decode the messages written in wavelengths and intensities and spectra. There's one more beautiful fact about light to share with you as you drift even closer to sleep, as your breathing becomes slower and more peaceful, as your body settles deeper into rest. Light doesn't just travel through empty space. It interacts with space itself. And space, as Einstein taught us, isn't a rigid, unchanging stage where events happen. Space is dynamic, flexible, responsive. Space can bend, stretch, and warp, especially near massive objects. And when space bends, light bends with it. This is one of the most profound and beautiful insights in all of physics, and it reveals something deep about the nature of reality itself. This is the heart of Einstein's general theory of relativity, published in 1915 after years of intense work. Massive objects like stars, planets, and galaxies don't just pull on other objects with some mysterious force acting at a distance. They actually curve the fabric of space-time around them. Space-time, the union of space and time into a single four-dimensional continuum, is not fixed. It's malleable. Mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. This is gravity, not as a force, but as geometry. Imagine space-time as a stretched rubber sheet, though this is only an analogy, a simplified visualization. Place a heavy ball on the sheet. The ball creates a dip, a curvature in the sheet. If you roll a smaller ball nearby, it will curve toward the heavy ball, not because the heavy ball is pulling it with a force, but because the sheet itself is curved. The smaller ball is following the straightest possible path through curved space, and that path appears curved to us. In the same way, massive objects curve space-time, and anything moving through that curved space-time, whether it's a planet, a comet, a spaceship, or even a beam of light, follows curved paths. These curved paths are called geodesics, the straightest possible routes through curved space. Light always travels along geodesics. In flat, empty space-time, far from any masses, geodesics are straight lines. Light goes in straight lines, as we've discussed. But near massive objects, space-time is curved, and the geodesics are curved too. Light follows those curves. It's not being pulled or pushed. It's simply following the natural geometry of space-time, the shape that mass has given to space. This means light can be deflected by gravity, bent around stars and galaxies, its path altered by the presence of mass. This prediction was one of the key tests of general relativity. In 1919, just a few years after Einstein published his theory, astronomers organized expeditions to observe a total solar eclipse. The eclipse was important because during totality, the sky darkens and stars become visible near the sun. Normally, you can't see stars near the sun because the sun's brightness overwhelms their faint light. But during an eclipse, with the sun's disk blocked, you can photograph stars that appear close to the sun in the sky. The light from those stars has to pass near the sun to reach Earth. Einstein's theory predicted that the sun's gravity would bend the starlight, making the stars appear slightly shifted from their true positions, shifted outward, away from the sun. Newtonian gravity also predicted a deflection, but only half as much. So this was a crucial test. 2 expeditions were organized, one to Sobral in Brazil and one to the island of Principe off the coast of West Africa. They photographed stars near the sun during the eclipse, and then, months later, photographed the same region of sky at night when the sun wasn't there. By comparing the 2 sets of photographs, they could measure how much the stars had appeared to shift. When the measurements were analyzed, they matched Einstein's predictions almost perfectly. The stars had shifted by about 1.75 arcseconds, a tiny angle, less than 1,000th of a degree, but measurable with the photographic techniques of the time. The sun had bent the light of distant stars. Space-time was curved. Gravity was geometry. News of this confirmation made headlines around the world. Einstein became an international celebrity overnight. His theory, which had seemed abstract and mathematical, was proven true by observation. General relativity was real. Since then, we've seen this effect, called gravitational lensing, many, many times on much larger scales. When a massive galaxy, or better yet, a cluster of galaxies containing thousands of galaxies, sits between us and a more distant galaxy, the foreground object's gravity bends the light from the background galaxy. This bending can create multiple images of the same distant galaxy arrayed around the lensing mass. Sometimes the background galaxy is stretched and distorted into arcs or rings. Sometimes the light is simply amplified, brightened, as the lensing mass acts like a natural telescope, focusing the light toward us. Gravitational lensing allows us to see objects that would otherwise be too faint or too distant to detect. There are famous examples with poetic names, images that have become iconic in astronomy. Einstein's cross formerly known as Q2237 Plum 305, is a quasar, a supermassive black hole at the center of a distant galaxy, producing enormous amounts of light as it consumes matter. A foreground galaxy lies almost directly between us and the quasar. The galaxy's gravity splits the quasar's light into 4 distinct images, arranged in a cross pattern around the galaxy's center. 4 images of the same quasar, all visible at once, because light is taking 4 different curved paths through space-time around the lensing galaxy. The Einstein ring, or one of many Einstein rings since several have been discovered, appears when the IC alignment is nearly perfect. If a distant galaxy lies almost directly behind a foreground massive object, and if the mass distribution is roughly symmetric, the background galaxy's light is smeared into a perfect circle around the foreground object. It looks like a glowing ring, the light from a single distant galaxy bent around a closer mass. These rings are hauntingly beautiful, perfect circles of light drawn by gravity. Gravitational lensing isn't just beautiful, it's scientifically invaluable. By studying how light is bent, astronomers can map the distribution of mass in the lensing object. This includes visible matter, stars and gas, but also dark matter, which doesn't emit or absorb light, but does have gravity. Dark matter is invisible, but its gravitational influence on light reveals its presence. By observing how lensing distorts background galaxies, researchers have created maps showing where dark matter is concentrated. These maps reveal that dark matter makes up most of the mass in galaxy clusters, far outweighing the visible stars and gas. The structure of the universe is held together by dark matter, and gravitational lensing is one of the main ways we study it. Even our own sun bends light just a little. During a solar eclipse, stars near the sun's edge appear shifted by about 1.75 arcseconds, as we mentioned. This is measurable, but small. Much stronger lensing happens around more massive objects. Galaxies can bend light by much larger amounts. Galaxy clusters can create spectacular lensing effects, with dozens or even hundreds of distorted, stretched, duplicated images of background galaxies, visible in a single telescope field of view. And black holes, with their immense gravity, bend light dramatically. Close to a black hole, space-time is curved so severely that light can be bent into spirals. Photons can be captured in unstable orbits around the black hole, circling it multiple times before either escaping or falling in. There's a region around a black hole at about 1.5 times the event horizon radius called the photon sphere, where light can orbit the black hole in a perfect circle. These orbits are unstable, though. Any tiny perturbation sends the photon either spiraling inward to be swallowed by the black hole or spiraling outward to escape into space. But for a moment, light can circle a black hole, trapped in gravity's grip. The famous image of a black hole released in April 2019 by the Event Horizon Telescope collaboration shows this lensing effect beautifully. The image shows the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. The black hole has a mass of about 6.5 billion suns, and its event horizon is about 20 billion kilometers across, roughly the size of our solar system. The image shows a dark central region, the black hole's shadow surrounded by a bright, asymmetric ring of light. That bright ring is light from gas swirling around the black hole, heated to billions of degrees by friction and compression as it spirals inward. The ring appears brightest on one side because the gas is moving close to the speed of light, and relativistic effects boost the brightness on the side moving toward us and dim it on the side moving away. But the key feature is the shadow, the dark region in the middle. That shadow is larger than the event horizon itself. It's about 2.6 times the size of the horizon. This happens because light rays that pass close to the black hole are bent so severely that they spiral inward and are captured, even if they don't technically cross the event horizon. The shadow is the region from which no light can escape outward to reach us. And here's something truly mind-bending. The bright ring of light includes photons that have traveled around the black hole. Some of the light in the ring comes from gas directly in front of the black hole, from our perspective. But some of it comes from gas behind the black hole, on the far side. That light has been bent around the black hole by its extreme gravity, brought into view. We're seeing behind the black hole and in front of it at the same time, because gravity has warped the light path so severely. It's a stunning visual demonstration of general relativity in action, of space-time curved into unimaginable shapes by mass and energy. Light, in this way, is a tracer of space-time's shape. Where gravity is strong, space-time is curved, and light follows those curves. Where gravity is weak, space-time is nearly flat, and light travels in nearly straight lines. Light obeys the geometry of the universe. It doesn't have a choice. It simply goes where space-time tells it to go, following the geodesics, the natural paths through whatever shape space-time happens to have. And in doing so, it reveals that geometry to us. We can't see space-time directly. It's not a thing we can touch or photograph. But we can see how light moves through it, and from that we can infer the curvature, the masses, the distribution of matter and energy, the hidden structures shaping the cosmos. Light is flexible, responsive, true to the nature of space itself. It doesn't resist the curvature. It doesn't fight against it. It flows along the paths that reality provides, and in flowing, it shows us the way. It carries information about everything it passes, every mass it skirts, every field it traverses. Light is honest. It reports truthfully about the universe it travels through. And we, by observing light with our telescopes and our eyes, by analyzing its wavelengths and its paths, we learn about the universe. We learn about stars and galaxies, about space and time, about the fundamental nature of reality, all through the simple act of looking at light. As we come to the end of our journey together, let's take a long, peaceful moment to reflect on everything we've explored, letting it all settle into your mind like soft snow falling on a quiet field. Light travels at a cosmic speed limit, 186,000 miles per second, carrying information across vast distances, connecting us to the farthest reaches of the universe. Every photon is a time traveler, bringing us visions of the past. When you look at stars, you're seeing them as they were years, centuries, millennia ago. You're looking backward through time, witnessing history written in light. Stars shine through nuclear fusion, the most elegant power source in nature, transforming matter into light in their cores, converting mass to energy through Einstein's beautiful equation. 4 hydrogen nuclei become 1 helium nucleus, and in that transformation, a tiny fraction of mass disappears, converted into photons, into heat, into the light that illuminates galaxies. Our sun does this 600 million tons at a time, every second, patiently burning its fuel over billions of years. And through this fusion, stars forge the elements that make up everything we know. Carbon, oxygen, iron, calcium, phosphorus, nitrogen, all the building blocks of rocky planets and living things, all created in stellar cores and supernova explosions. You are made of these elements. You are made of stardust, quite literally. The atoms in your body, except for hydrogen, were all created inside stars, in their fiery hearts or in their explosive deaths, and then scattered across space to eventually become part of you. Light exists in forms we can see and forms we cannot. Visible light, the rainbow we know, is only a tiny sliver of the electromagnetic spectrum. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, all of it is light, electromagnetic radiation, differing only in wavelength and energy. We live in an ocean of invisible light, passing through us constantly, carrying information, energy, warmth. Infrared warms us. Ultraviolet gives us vitamin D. Radio waves carry voices and data through the air. We're surrounded by light we cannot see, and that's a humbling thought. Our eyes show us only the smallest fraction of what's really there. But we've learned to build instruments, extensions of our senses, to detect the invisible, to translate it into something we can understand. We've learned to see beyond our limitations. Shadows teach us that light moves in straight lines, creating darkness as proof of its passage, the negative space that defines the positive. Every shadow has structure, an umbra and a penumbra, regions of total and partial darkness. Shadows change with the angle of the light, stretching long in the morning and evening, shrinking at noon. Ancient humans used shadows to tell time, to track the seasons, to understand the motion of the sun across the sky. Sundials are among the oldest scientific instruments, simple but elegant, using geometry and light to measure the passage of hours. Eclipses are shadows on a grand scale, cosmic alignments that reveal hidden wonders. Lunar eclipses show us Earth's shadow falling on the moon, turning it red with the light of all our sunrises and sunsets. Solar eclipses reveal the sun's corona, the ghostly outer atmosphere normally invisible, made visible when the moon blocks the brilliant photosphere. We're lucky to live in an era when total solar eclipses are possible, when the moon is just the right size and distance to perfectly cover the sun. This won't last forever. The moon is slowly drifting away, and in the far future, there will be no more total eclipses. We're living in a special time, cosmically speaking. Stars are born in clouds, dark nebulae of gas and dust, where gravity slowly gathers material together until fusion ignites and a new star lights up. Stars live for billions or even trillions of years, depending on their mass, fusing hydrogen in their cores, holding themselves up against gravity through the pressure of the energy they generate. And stars die in spectacular ways, enriching the universe with their remains. Sun-like stars swell into red giants and then gently puff away their outer layers, creating planetary nebulae of breathtaking beauty, leaving behind white dwarfs that slowly cool over eons. Massive stars explode in supernovae, outshining galaxies, creating neutron stars and black holes, scattering heavy elements into space. And from this enriched material, new stars form, and planets, and eventually life. It's a cycle, a grand cosmic recycling program, each generation of stars building on the work of the previous generation. And light itself is shaped by gravity, bent by the curvature of space-time, revealing the hidden architecture of reality. Massive objects warp space around them, and light follows the curves, the geodesics, the natural paths through space-time's geometry. Gravitational lensing shows us distant galaxies we couldn't otherwise see, reveals the distribution of dark matter, proves that space is not fixed but flexible. Black holes bend light so severely that photons can orbit them, and we can see the light from gas behind a black hole brought around into view. An impossible sight made possible by extreme gravity. Light is a tracer of space-time, an honest messenger that reports faithfully about the structure of the cosmos. All of this is happening right now, all around you, every moment of every day and night. As you lie here, relaxed and peaceful, photons are streaming through space, carrying starlight from distant suns, some of them traveling for thousands or millions of years to reach Earth. Right now, light from Betelgeuse, light that left that star over 600 years ago, is arriving at Earth, entering our atmosphere, scattering in the air, some of it eventually reaching the ground. That light has been traveling since the Middle Ages, crossing the vast emptiness between stars, just to arrive here, now, and it will keep arriving for years to come. An endless stream of photons from the past. Shadows are shifting constantly as Earth turns, as the sun appears to move across the sky, as objects move through space. The shadow of your house is stretching and shrinking and rotating, a slow dance choreographed by the planet's rotation. Somewhere on Earth right now, someone is witnessing an eclipse, standing in a shadow cast across interplanetary space, experiencing one of nature's most profound spectacles. Somewhere, a star is being born, fusion igniting for the first time in a protostar's core, adding a new light to the galaxy. Somewhere, a star is dying, exploding in a supernova, forging gold and uranium, scattering them into space to become part of future planets and future life. Atoms in the sun's core are fusing right now, this very instant, releasing the energy that will warm your skin tomorrow after it spends 8 minutes traveling from sun to Earth. Massive objects are bending light across cosmic distances, galaxies acting as natural telescopes, focusing light from the early universe toward our telescopes. The universe is alive with light, with motion, with transformation, with the slow, patient work of stars converting matter into energy and energy into complexity. And you're part of it. You're not an observer standing outside the universe looking in. You're an integral piece of it, woven into the cosmic tapestry. You're an observer, yes, but more than that. You're a collection of stardust arranged in such a way that you can perceive light, understand it, marvel at it. You can think about photons and wavelengths. You can contemplate fusion and space-time curvature. You can appreciate the beauty of a shadow or the color of a sunset. The universe has arranged itself so that it can know itself, experience itself through you. You're a temporary pattern in the cosmic flow, a brief arrangement of matter and energy that has the extraordinary gift of awareness. The ability to look at a star and wonder about its nature, to see light and understand what it is and where it came from. And in this moment, relaxed and quiet, you're connected to everything, to the light streaming past you, to the stars shining overhead, to the shadows they cast, to the atoms in your body that were forged in stellar cores billions of years ago. You're connected through physics, through chemistry, through the laws of nature that govern photons and particles and planets. You're part of one continuous interconnected whole. The same forces that shape stars and bend light also shape you, govern your existence, make you possible. The same atoms that glow in distant nebulae make up your body. The same physics that governs photons governs every cell, every thought, every breath you take. Let yourself rest in that connection, in that belonging. There's nowhere you need to be right now. There's nothing you need to do. The universe is unfolding exactly as it should, following the laws of physics, following the curvature of space-time, following the paths laid down by gravity and quantum mechanics and thermodynamics. Stars are shining, light is traveling, shadows are forming and dissolving, atoms are fusing, planets are turning, galaxies are spinning, and you, here, now, are exactly where you belong, lying peacefully, breathing slowly, part of it all. The stars don't judge you. They don't demand anything from you. They simply shine, doing what stars do, converting mass to energy, illuminating the cosmos. Light doesn't ask for permission. It simply travels, carrying information, connecting distant points in space. Shadows don't apologize for being dark. They simply exist, the natural consequence of light encountering opacity. Nature doesn't require anything from you except that you exist, and you're doing that perfectly right now. You're existing, you're being, and that's enough. That's more than enough. That's everything. You can let go of any tension, any worry, any thought about what you should be doing or where you should be. Right now, you're here, and here is where you're meant to be. The universe brought you here through an unbroken chain of cause and effect, stretching back to the Big Bang, through the formation of stars and planets, through billions of years of evolution, through the chance meetings of your ancestors, through every moment of your life leading to this one. You're the result of 14 billion years of cosmic history. You're valuable simply because you exist. You don't have to earn your place in the universe. You already have it. You're already home. And you're safe. The universe is vast, but it's not hostile. It's neutral, following its laws, unfolding its patterns. Stars will continue to shine. Light will continue to travel. The laws of physics will continue to operate, reliable and consistent. The sun will rise tomorrow. The stars will come out tomorrow night. Seasons will change. The cycle will continue. There's a stability in that, a reliability. The universe is dependable in its own way. It does what it does, patiently, endlessly, without hurry or worry. And you can rest in that dependability. Breathe slowly. Let your body sink even deeper into comfort. Let your muscles release any remaining tension. Let your mind drift, peaceful and calm, surrounded by the knowledge that you're part of something vast and beautiful and endlessly mysterious. You don't have to understand it all. No one understands it all. The universe is full of mysteries still unsolved, questions still unanswered. Dark matter, dark energy, the nature of time, the origin of quantum mechanics, the fate of the universe, the possibility of life elsewhere. We don't know everything. We never will. And that's okay. That's part of the beauty. There's always more to discover, more to wonder about, more mystery waiting just beyond the edge of our understanding. But what we do know is extraordinary. We know about light, about stars, about shadows. We know about fusion and space-time and the speed of photons. We know we're made of stardust. We know light is both wave and particle. We know shadows reveal the shape of worlds. We know stars are born and live and die. We know gravity bends light. We know the universe is connected, interwoven, a single magnificent whole. And we know you're part of it. That knowledge is enough for tonight. More than enough. It's a gift, really, to understand even this much about the cosmos. The stars will still be there when you wake. The light will still be traveling through space, bringing messages from distant suns. Shadows will still be forming wherever light encounters opacity. Fusion will still be happening in stellar cores, creating the energy that powers the universe. And you'll still be here, made of stardust, carrying the legacy of ancient stars within every cell of your body, a brief but brilliant pattern in the cosmic flow. Rest now. Let the gentle facts about light, stars and shadows carry you into deep, peaceful sleep. Let yourself drift on the knowledge that you're connected to everything, part of the grand cosmic story, a child of the stars. You're safe. You're connected. You're home in the cosmos. The universe knows you. You are known. You are one with the light, one with the stars, one with the shadows. And in that oneness there is perfect peace. Close your eyes or keep them softly open. It doesn't matter. Let your breathing become automatic, easy, requiring no thought. Let sleep come naturally, gently, like starlight arriving after a long journey across space. You've traveled through the cosmos tonight, through time and space, through light and shadow, through birth and death of stars. And now you can rest. The journey is complete for tonight. Good night. Sleep well. Dream of stars.